Get ready, because in this section we're diving into the ionic compounds, see what they're made of, see how to balance their charges, and how to name them. So the vocabulary for this section will include ion, cation, anion, polyatomic ion, and the electrostatic force. Let's take a moment to review what ions are. I know that we talked about this a little while back when we were going through Unit 5, and we talked about the ionic compounds, but I think it's useful to just quickly review on this so we have a fresh take on what we're seeing in this. So remember that when we see atoms in their ground state, the way we find them on the periodic table is that they are neutral in charge because they have the same number of protons and electrons. Remember that protons are positive and electrons are negative. And so when you have the same number, they both cancel out. So in total, our ground state elements and atoms have no charge. So let's take a quick look at this. So if we're looking at sodium and we have this diagram of sodium on here, we know that its atomic number is 11. So in the ground state, it will have 11 protons and 11 electrons. Again, protons are positive, electrons are negative. So if we have plus 11 minus 11, overall we get 0. This is what we say that the ground state atoms are neutral in charge. But remember that when we are dealing with ionic bonds, we get a transfer of electrons. So I have that in this picture right here, where the valence electron in this metal atom is being transferred over to the non-metal atom. And so I think it's useful to see it in action. So let me go ahead and check out this graphic that I have going on. I'll wait for it to reset and I'll start talking over it again. So here we have the two atoms in their ground state, and this valence electron on sodium is being transferred over to the fluorine, and so it's affecting our total count of electrons. So let's go ahead and see that in action over here. All right, so we're turning back to this graphic. So we start with this top electron in sodium, and we're getting rid of it. So it's going to affect our total count of electrons. Our protons haven't changed. We still have 11 protons, but with only 10 electrons, if we try to do that same calculation, plus 11 minus 10, we get a remainder of positive 1, which means that when we lost one of our negative electrons, the positive charge became a lot stronger in our sodium, and it overall gained a plus 1 charge. And we can do the same thing to the chlorine. So right here, chlorine its atomic number is 17, which means it will have 17 protons and 17 electrons. Protons are positive, electrons are negative. 17 minus 17 is overall 0. But when we are dealing in an ionic bond, an ionic transfer, this chlorine now gains a new electron. So our new image of chlorine will look like this, with 17 protons and 18 electrons. And again, if we try to do the quick math over here, a positive 17 minus 18, overall we have a negative 1 because we have an extra electron. And now we give our atoms a different name after this happens. When they are not balanced and they have either gained or lost electrons, we now call them an ion, and that means that they have a charge. Remember that ion is not specific, could be positive, could be negative. It's just saying that it has a charge. When we do this, we only count the number of electrons, because protons, we can't change that without changing the element. But then going back to the thing on ions, remember that we can have two types of ions. We can have the positive ions, we call those cations, that we get after we lose electrons. And then the when we gain electrons, remember these are negative, so we are adding a negative charge. We call this the anion. And then a useful way to remember this is that metals in general will always lose the electrons, and the non-metals will tend to gain the electrons. And again, this is all because of the differences in electronegativity, but we're not going to go into more detail than that. And if you need a useful, simple way to remember this, which ones are positive, which ones are negative, remember that the cations have a positive charge. Now let's dive a little bit deeper into this ionic charge. So the way that we determine the ionic charge, just to keep it pretty simple, it will depend on the number of valence electrons that we get from the elements. But I should say that it's also a little bit different than just knowing the number of valence electrons. So let's see what's going on with that. Remember that groups 1, 2, and 3 on the periodic table, you will see that they will tend to give away a certain number of electrons, and they become positive because they're giving away their negative electrons. Now, for groups 5, 6, and 7 on the periodic table, because they have very strong electronegativities, they will tend to gain those electrons, and because they're getting more negative particles, they are becoming negative. They become our anions. So let's go ahead and look at this table. We have a trend for the ionic charge, and I'll explain what all this means. So again, we talked about groups 1, 2, and 3 will become positive. So let's see why that is. So let's see, if we're looking at this group 1 column over here, we know they have one valence electron, and that's what I have written up here. But what they do is that they have one electron to give away. When they lose that electron, they are going up in charge by 1. So that's why we say that group 1 will have a charge of positive 1 once it involves an ionic transfer. Now, if we move on to group number 2, they have 2 electrons to give away. So if they're giving away 2 positive particles, that means they're gaining 2 positive charges. And so our group 2 will have a charge of positive 2. And this continues on with group number 3 on the periodic table. Remember to skip the transition metals. So group 3 for aluminum and gallium, again, they have 3 electrons to give away. So they will gain a charge of positive 3. Now, when we get to group 5, things start to get a little bit different, and it starts to go in reverse, because when groups 1, 2, and 3 give away their electrons, groups 5, 6, and 7 can pick it up. So when they pick up the electron, they are getting more negative particles, and they are becoming negatively charged. That's why with group number 7, elements like nitrogen and phosphorus, they can gain 3 electrons. So when they do, they get a charge of -3. If we continue on, for group number 6, oxygen, sulfur, and selenium, they can gain 2 electrons, and when they do that, they get a charge of -2. And finally, with group number 7, the halogens, fluorine, chlorine, bromine, and iodine, they can gain 1 electron, and they gain a charge of -1 when they have that 1 extra electron. Notice that for the noble gases, we have 0 on them because they already have a full octet, and they don't gain or lose any electrons. Now, these charge numbers that we're talking about, they have a little more complicated name. They have another use for it too, but we're not going to get into it. But it's called the oxidation states. So just remember that the charge numbers are also called oxidation states, and it goes off how many electrons they either give away or they can receive, which goes along with how many valence electrons they will have. Now, it's an important concept, and it will make it a lot easier if we can remember this. So that's why I want you to make a big note of it, put it in a box, highlight it, something like that, to where you can easily go to this section on your notes. And it helps us to understand these diagrams over here. So like the example that we had before, where we're having an ionic transfer between sodium and chlorine, we know that sodium is giving away 1 valence electron, and that's why we'll gain a charge of +1. And chlorine is gaining that 1 electron, so that's why it's gaining a charge of -1. Now, what I've been telling you all this time is that for the transition metals, we always skip them, especially with the valence electrons, because I've told you before, they're funky, they're weird, it's hard to predict what they do, but we're finally going to take a look at them a little bit more closely. If you're looking at this graphic earlier before, you might have noticed that I don't have any transition metals on these, or I should say most transition metals aren't on here. The reason for that is that a lot of transition metals can have multiple oxidation states, or that they can receive or give away different amounts of electrons depending on the context of a reaction. And so I know that's complicated to think about, it's complicated to predict, but luckily they're pretty consistent in what they do. So let's go ahead and look at that. So I have this new table on here where I have all my different transition metals that we'll be seeing, the common ones, and what their possible oxidation states are. Now, I know that this is a very long list, and it might be a lot to memorize, but luckily it's a very shortcut, very simple way to remember these, because for these transition metals, notice that we have something in parentheses. It's either II, III, or it might be IV, something like that. So these are just Roman numerals, and those Roman numerals are important because they're telling us exactly what the charge on that atom is. So even if you don't remember this table, as long as you know that the Roman numeral is the same as the charge number, you'll be pretty okay. All right, so let's look at an example of these without having to go through this entire table. So if we look at iron, there's two versions of iron we can have. So for iron 2, iron II, that means that it has a charge of positive 2, and that's what I have here on the table as well. But if we had iron 3, 3 I's inside the parentheses for the Roman numeral, that means that this iron has a charge of positive 3. If we keep going along with it, lead 2 has a charge of positive 2, and lead 4 has a charge of positive 4. So it's very straightforward, but it's also important to notice that this might get a little bit tricky, but the Roman numerals that we have for our atoms don't tell us what the number of atoms in a compound that we have. So we'll be looking at some chemical formulas here in a few slides, so I'll bring this up again, but I just wanted to make sure that you get it in your notes now too. Let's make this a little bit more interesting. We're going to throw in a little bit of a curveball to go along with our ionic compounds, because so far we've only talked about metals and nonmetals, right? In an ionic compound, you have one atom that's metal, you have one atom that is a nonmetal. Well, there's actually this whole other class of ions that we can have, and these are called the polyatomics. And what they are is basically they're ions that are technically covalent compounds, but because of the way that their electron stabilities work, they actually carry a charge like ionic compounds do. All right, so just what we need to know from this is that we have different ions that can, different molecules that can actually act as ions. And if you break down the name of the polyatomic, poly in Greek it's a prefix that means many, and atomics that comes from atoms. So we're basically saying that we have ions that are made of many atoms. And the important thing is that even though they're made of many atoms, they act as a single unit. They're not individual ions by themselves. So let's look at some examples to actually make sense of that. Here I have a graphic that actually shows you what the molecules look like, what their structures are, and you can see that, again, I have this ammonium ion where I have nitrogen covalently bonded to 4 hydrogens, but it carries an electrical charge. And that's interesting to see. And make sure that you remember that these don't break up easily, and they act as a single unit. All right, and so, but more useful will be this list that I have over here. I'll be giving you a reference with all these so you don't have to memorize them, but it's important to know where they are and what you're looking for when you use this. One thing I want to point out is that we have some very common pairings. They're very similar, so it might be confusing this way. But an example here, we have nitrate and we have nitrite. They're two very similar words. They're only one letter off, A and I, but their chemical structures are a little bit different. So notice that for the nitrate, it will have 1 nitrogen and 3 oxygens with 1 negative charge, and nitrite has, again, 1 nitrogen and a negative charge, but there's a difference in the number of oxygens. Nitrite only has 2. And this is true for a lot of these pairings. When you see 8 versus ite, is that the 8 compounds, so in this case sulfate, has more oxygens than sulfite. Sulfate will have 4 oxygen, sulfite has 3 oxygens. And then there's also phosphate and phosphite, 4 oxygens versus 3 oxygens. So just make sure you keep that in mind whenever you're looking for a phosphorus ion or a sulfur ion. Remember that there's 2 versions of it, and look out for the oxygens. Then one last compound or ion to point out is the hydroxide ion. It is OH, has a -1 charge, and it's important to point out because we'll be seeing this a lot from here on out. So make sure that whenever you hear hydroxide, you're always thinking of an OH, not just hydrogen or oxygen by itself. Now let's take a look at charge balancing, because as we've discussed before, ionic compounds are held together by the electrostatic force, meaning that the individual ions have positive and negative charges, and this difference in charges is what holds them together. Remember that opposites attract, so positive ions will always pair with negative ions, and negative ions pair with positive ions. But what ends up happening is that our ionic compounds overall are neutral in charge, meaning that the positive charges are exactly matched by the negative charges, and they cancel out in a sense. So let's take a look at what this would look like. So let's turn back to this graphic of the ionic charge for a little bit of assistance, and let's actually look at an example on this. Let's say that we want to make a compound of sodium and chlorine. This will be a An ionic compound, because sodium is a metal on the left side, chlorine is a non-metal on the right side. And we can know what their charges will be by looking at this chart. So if we look for sodium, it is over here in the first column, which means that it will have a positive 1 charge. So I'll just add a positive sign to my sodium. If I don't add a number, that's implied that it's a 1. If it's 2 or higher, you have to specify what number it is. But that being said, sodium only gets a positive 1 charge. Chlorine on the right-hand side will get a negative 1 charge. So I'll mark those. So now I know what the charges on the individual atoms are. I need to know what the total charge for the compound will be. So if I take this, I have my positive 1 from sodium, and I subtract 1 because I have negative 1 from chlorine. And so 1 minus 1 gives me a total of 0. That's how I know that this ionic compound is balanced. And to write out its chemical formula, I would just put in 1 Na and 1 Cl written together like this. All right, but let's do an example that's a little bit more complicated than that, something that's not a 1-to-1 balancing ratio. Let's say that we stick with chlorine because we already know what the charge on chlorine is. We're familiar with it. But let's add in aluminum. If I look for aluminum on the periodic table, it is in this third column, Al, number 13, and we see that it will have a charge of positive 3. So let's go ahead and add in those charges. Chlorine with a minus 1 charge, aluminum with a positive 3 charge. Let's say that we wanted to balance these out. Well, if we only had 1 atom of aluminum and 1 atom of chlorine, if we do this math, 3 minus 1, we have a positive 2 charge. And this is not a balanced compound. So this can't be the final form of the compound. So let's try that again. Now, for these, we can't change the elements we're using, and we can't change their individual charges. But what we can do is control how many ions of each type we have. So in this case, because I have more positive charge on aluminum, I need more negatives, so I'm going to add in another chlorine. So now I have 1 atom of aluminum worth positive 3 and 2 chlorines each worth negative 1. So if I do that math, 3 minus 1 from the chlorines, I get positive 1. That's closer, but still not 0 that I want for a valid ionic compound. So let's take that off and let's try that one more time. Since I'm only off by 1, I'm going to add a third chlorine, and we'll see how this works out. So we have the positive 3 from aluminum, and then we have negative 1 for 3 chlorine. So 3 minus 1 minus 1 minus 1 totals 0. And then, yes, this is the right number of ions that I need for a valid ionic compound of aluminum and chlorine. Now, to write the chemical formula for this one, I would take just 1 aluminum, Al, and I would pair that with Cl and use a subscript 3 to show that I needed 3 chlorine ions. If you're thinking that last way to solve that ionic balance was a lot of trial and error and a lot of waste of time, I agree with you. So that's why I want to show you this other way to do it. There's a lot less trial and error involved, and it's more precise. And it's called the crisscross method. So it's very simple to use. We only go through 2 steps on this. So for the first step, we need to know what the charges of each ion is. And in the second step, we're going to use that charge number and pair it to the opposite element for the subscript. So let's actually see that in action. So if I bring back that same example from before, aluminum and chlorine, I want to know how many aluminum ions and chlorine ions I need for a balanced compound. All right, so on this, I'm going to focus on the numbers that go with the charges. It doesn't matter if they're positive or negative. In this case, I just need to know that aluminum has 3 and chlorine has 1. So if I start with aluminum here, I'm going to take the number from chlorine and I'm going to pair it to aluminum for the subscript. But remember that for 1, we don't say anything in the subscript. So to begin writing the chemical formula, I would just write Al for aluminum. Now for chlorine, I'm going to take the positive 3 from aluminum, and I'm going to pair it to the chlorine for its subscript. So for chlorine, I will write Cl3 for the balanced chemical formula. And if I do that math again, I know that my chlorine is worth positive 3. Chlorine, they are each worth 1, but because there's 3 of them, I will multiply that by 3. So 3 minus 3 gives me a total of 0. And when I know that this is a balanced ionic compound. Lastly, let's get into the naming of these compounds. And so let me put you on alert and start by saying that ionic compounds follow different rules for naming than covalent compounds. So make sure that you are setting up two different rule sets for these compounds and that you don't mix them up. All right, so to name the ionic compounds, we go through 4 simple steps, and let's go ahead and do an example as we're going through these rules for the first time. So let's bring back that example before of aluminum and chlorine and see how we would give it a name. The first step is that we need to name the metal element. So in this case, aluminum. Very simple. I'll just write down aluminum. Step 1, done. Pretty easy so far. Step 2 is that I need to name the non-metal element of it. So now I have chlorine on here, so I'll go ahead and write in chlorine. But I can't just name it aluminum chlorine because that's not a chemical name. I need something to tell me that these atoms and ions are bonded together. And that's where step number 3 comes in. I need to take the last syllable and change it to IDE. So in this case, I can't have chlorine, but it will become chloride. And it's pronounced a little bit different, so make sure you take note of that too. And in the final step, it's really more of a reminder. It's not something we have to do, but we just need to remember that the number of ions in this one doesn't matter. This is where it's different from the covalent compounds. Whereas for the covalent compounds, this Cl3, you would say that it was trichloride. But if it's an ionic compound, you don't use that tri. You don't use any of the number prefixes because we always balance out the charges on our ionic compounds. Now, this is very simple for when we have ions that have a predictable charge, but as we talked about with the transition metals, is that sometimes they can be different. So let's look at one of those and see what happens to it. If we have iron and oxygen in a compound, we have one iron ion and one oxygen ion. How would we name this, especially when we know that there can be different types of iron? So, well, first let's start with the first step where we just name the metal element. This is still the same thing, but we go through a little bit of a different rule since it is a transition metal. Remember that for the transition metals, we need to use a Roman numeral that tells us the charge of it. So again, I have here iron 2 and iron 3 with a positive 2 and a positive 3 charge. So how do you know which iron you have in this case? It's not telling you anything other than it's just iron. So in order to tell which type of iron it is, I need to look at oxygen. Oxygen doesn't have a multiple oxidation state. It will always have the same thing. So if I bring back this graphic and I look for oxygen, it is right here, number 8, and it has a charge of -2. So I can give it that -2 charge, and I can see from this chemical formula that there's one oxygen and one iron, which means that they are balancing out perfectly. That means that iron will have the opposite charge of oxygen. So if this oxygen has a -2, we give this iron a +2 charge. And if it has a +2 charge, that means that it is iron Roman numeral 2. So I'll write that down. Iron 2, remember that the Roman numerals go in parentheses, and then I can continue on to my step number 2. That's name the non-metal element, and that's oxygen. And finally, I need to adjust the name of oxygen to an IDE ending. So I'm going to take oxygen, replace that with oxide, and so the name of this compound is iron 2 oxide. And notice that even though this is iron 2, there's only one iron ion because these Roman numerals don't tell you the atoms we have. It only tells you the type of atoms that we have. And one last example, so we have good practice on this and a good base to go forward with this. You might notice that there's something different going on with this one, so let's talk about that. So let's go ahead and just go through the first step because nothing changes on this. Magnesium, it's not a transition metal. It's right here in the second column, so I can just go ahead and name it magnesium. I'm done with the first step, but when it comes to the second step, notice that I have more than just one atom. I have oxygen and hydrogen, and notice that it's put around a parentheses. That's an important clue because when you have these parentheses, it's saying that what's inside the parentheses is acting as a unit. In other words, it's a polyatomic ion. So in this case, I have the OH polyatomic ion, and I have 2 units of that to pair with the magnesium. Now remember that for the polyatomic ions, we don't name it oxygen and hydrogen. We need to use its polyatomic name, and in this case, here it is, OH. It's called hydroxide. So for my chemical name, I will continue with step number 2 by naming it hydroxide. Step number 3 is that we need to change it to an IDE ending, but notice that hydroxide already has that IDE ending. So there's nothing that I need to change about hydroxide. This compound is just named magnesium hydroxide, but notice that there's nothing that tells you that there's two. Remember that you will tell this from the charge balance on the individual ions. All right, so that wraps up everything that we're going into for the nomenclature. I know that it might seem kind of heavy, but it just takes some practice to get used to it and to recognize the patterns in it. So that's exactly what we'll be doing next.